let's recall what happens at the beginning of the course. We wanted to analyze correctness of the arguments, or truth and false value of the statements, and then we developed a little algebra that sometimes helps us to do this in the abstract way to check in a safer way truthness of a statement. Is that clear? But now we will look at a different application of the same object. So what is the application? The application is basically people noticed that there are some digital circuits that actually behave in a similar way as statements and can use the same algebra that we developed last week and this week. So what would that be? Suppose that we connect two sources of electricity, and we for example connect them in a serial connection. What happens, or not two sources, but let's say two switches. Switches are better. Let's say we have a switch here, and we have a switch here, but I didn't connect them in serial connection, I connected them in what? Parallel connection. And then what? If you want the current to go through this system, this time it will not go through the system. Why? Because both switches are off. Do you agree? But then if I turn one of the switches on, then I will have current through the whole little circuit. Do you agree? So what is that? Does that remind you of one operation that we studied? Or. So this looks like it could be coded with P or Q. And then P and Q are individual status of those two switches, and P or Q is so this is P switch, this is Q switch. And then different position of the switches, those are different lines in the table. Does it make sense? All right. The same way, if I connect two switches in serial connection, then what would happen? It behaves like that. So we can use the machinery that we developed to analyze the circuits connecting very complicated switches. Why is that so important for us? Because actually that's how you have processor constructed from little circuits combined or connected in a way to perform certain operations. So we are trying to understand, for example, and that's the goal for the whole day for two sections that we do today, how can a processor add two numbers? So how do we accomplish for a processor to execute like 23 plus negative 57? So that's the goal for today. So first we will look at this in these elementary circuits. Let me pull out the screen. All right. Oh, here are the circuits. All right. So let's first disregard this construction that we just analyzed here in switches. We will we'll actually talk about the gates. So disregarding how are they constructed, we'll just say whatever it is, this symbol will denote the AND gate. So what is the AND gate? This is the little device that does the following. That here you put the inputs. Do you see the inputs? And here is the output. So this is the device, however it is connected, and that is actually in a way serial connection, that this will have a current only in one case. And what is that one case? If you put current on both those inputs. Is that clear? This is the OR gate. What is OR gate doing? The same what we explained here without explaining the internal structure. So it will have a current on the output if one of them is OR. Is that clear? What about this one? We also need this one. This one you can say that's inverter. So what is the inverter doing? It's like, if you have on signal here, it will produce what? Off. And the other way around. If it's off, it will be on. So actually, like negation, switches to the opposite. Is that clear? So question is, if we have these three types of little devices, if we connect them, what can we accomplish? Okay. Anything that we want, and we want to see how to do the modeling and how to do the wiring. So let's see first. So here's the example on the screen. So let's answer the question that's there. So what would? All right, so here is a circuit, and we have inputs P is 0, Q is 0, and R is 0. Let's see if we understand what happened here. So we labeled, here when I labeled this input Q here and Q here, what am I saying? Always have the same value. How can we assume that? Just there is a source, and then both of them are connected to the same source. Do you agree? So if that source provides on, they are both on. So they always have the same value. What about P and R? They could be completely unrelated things. So what did we do here? This is an OR, this is an AND, this is inverter, and this is OR. So if I feed all three zeros, what will happen? This AND gate will produce what? The opposite. First, AND gate first. On 2 zeros, it will produce 0 here, do you agree? And then inverter will produce what? 1. And what is this? Or if I have 1 here, I don't care what happens up there. I can immediately say what? That this circuit will be on under this feeding of the inputs. Is that clear to everybody?
What defines it as to be 1? Is it going to the NOT gate?
This, because you see, maybe I didn't emphasize it enough. There is a particular valuation that's on the previous page. Valuation says all three letters P, Q, and R are 0. Do you see that?
Oh, okay.
So then Q and R make 0 or off, and then inverter will make it on, and then OR gate will make it also on.
That's just Boolean values.
Yes. So generally, what's the main thing? Can we always, whenever we work with the circuits, actually construct the appropriate formula from propositional calculus and then do the tables the same way as before? Yes or no? And that's the skill that we want to learn here so that we connect with the material that we are studying here. Let me make the appropriate formula for this. So what would that be? So first one is what? P or Q. So that's that upper sub-formula. And then there is OR between that one and whatever's below. What's below? Q and R on the bottom, and the negation on that one. Do you agree? And then OR between them. Is that clear to everybody? So generally, I can always translate that. So now I have propositional formula that's coding this circuit. And then the question now with putting certain values on the inputs is the same as calculating the value of the formula under certain evaluation of propositional variables. Is that clear? So that's it. Now we can use our old machinery on this. Although, I'm not going to insist on it, but maybe from time to time or during this homework, just try to practice how to draw these symbols so that they are readable. So kind of, if you ever take that course, and probably many of you will take some circuits course even either here or somewhere else. So it's a good idea to kind of be able to visualize those as well. All right. For example, that's happening here. We want to go in the other direction. So we want to construct a circuit corresponding to the formula. So first we did formula to circuit. How about circle to a formula? So what are we going to do? So what? First one is P and the not Q. So what are we going to do if we have P here? Sometimes people actually take P, Q, and R from one spot and carry them around, and that's how we can do it maybe. So P and Q are here, and they are the only letters. So what do I need? I need Q, and I need one inverter. Do you agree? And then on a P and that inverter, here they are, P and inverter. How do I connect them? And so that would be. So here is and. I like to write letters because if it's not clear how my drawing goes, this is safer. And then what about the other one? Not P and Q. So now I will lead from here. I will lead P through inverter. And I will lead Q normally before inverter. So this is what? Not P and Q. So I will now feed those two into what? Again into AND. So here is AND. Be careful that you are sure that it really, if you are going through inverter or not as needed, and then I'll do OR. Or here's your AND. So here is the gate. So you don't need to label here. You can lead them from the source of the signal, and then that works as well. Good. Now let's address a more interesting issue, and it's very important that we learn the notion of a recognizer. So what is the recognizer? A recognizer is generally we can use it both for circuits and for the formula. A recognizer is a type of the formula that's true only in one line in the table. And actually you can know exactly which line it is. So here it is. I'll formulate it in terms of propositional terms, or we can read it in the circuit terms. Question. Find the formula which is true only if and only if P, what did I want recognizer there? Doesn't matter. Oops. P0, Q0, R1. You see, here I somehow switched from talking about true, false into what? 0 and 1, or also another one is on, off. So 1 stands for on or true, 0 stands for off or false. So I want a formula which is true only if P is what? False, Q is false, R is true. Can you write that formula? So formula that kind of, will be true on those three values, but only then. What is the formula that's very exclusively true? Is that conjunction or disjunction? And. So I want a formula that's what? To be true, it must have R. So would it be and R, yes or no? So this formula will survive only if you provide R to be 1. But what on Q? Not Q, exactly. If you look at this formula, then what happens? If you want this, that's why it's a recognizer, because it forces the valuation. There's only one valuation that makes it true. What is that valuation? R must be what? True. Q must be what? True or false? False, and negation makes it true. P has to be what? False. So generally, how do you make a recognizer? What will be the recipe? If you see true on valuation, you take a letter. If you see false, you take what? Negation of the letter, and then you take conjunction of all those. Is that clear? So those are called recognizer formulas, because, as I said, they kind of code in that formula one valuation line. All right. An idea of recognizer can help us to solve problems like this. You have 3 switches. Design a circuit so that the bulb is off when they are all off, and every switching of individual switches changes the bulb status. Do you understand? That's how, like you have 3 floors, and then whenever, you know how it works. If you control one bulb from all 3, what happens? Whatever it is, when you switch a circuit, whatever position it is, it will do the opposite. Do you agree? So how would you connect those switches so that they do that? So I want, once again, you have 3 switches. Design a circuit so that the bulb is off when they are all off, and every switching of individual switches changes the bulb status. So here is how I see that question. Instead of talking about the bulbs and switches, I want to talk about propositional formulas. So on that formula, I'll say the following. So here it is. So question, it says what? Bulb is off when all switches are off, and every change changes the bulb, like something like that. So what happens? For 3 switches, I have how many cases? 8. Those are valuations, but as I said, switches, valuations are today's switches. So I go what? True. 4 T's, 4 F's. Then 2, 2, and then 1 each. And then what happens? What they told me is, so what is the value of my formula? So let's say formula, value of the formula. That's how it will be recorded. On the bottom, I know when they're all switched off, what do I want? The bulb to be on or off? Off, so I want false. What happens here? From that situation, I switch to one bulb. So when one bulb is on, what happens?
The light should come on.
It comes on. So where is that? Here it's true. Where else? Where only one. Here is one is true. And then where else is also one? Yeah. It's quite important that you line these things carefully, and I didn't do it. Yeah, so here it is 2 here, at least 2 by 2. Looks like that. Shh. No, I have to line them up better. You just cannot. So here it is. So next 2 and last 2. So this would be FF, FF, and this would be what? TTFF, and finally TF. And we said here we want false. Here there's one true, so it will be true or on. What about here on this line? One true, so it will be true. And then what happens on this line then? False, because now I switched another one, so that will be a switch. So generally what it says is when you have 2, what about this one? True. What about this one? False. What about this one? False, and this is true. Basically, if you have 3 switches on, you are on. If you have odd number of switches on, you are on. If you have even number, you are off. Do you agree? So question is, how do I connect them?
Find values for each where it's true.
Uh-huh.
And you do the minterm just like we've done it there, and then you form together.
Very nice. For each line, build a recognizer. So here it is. You record all the rows when you have true, when you want on. Is this on, yes or no? Circle it, or check it, or put a star. No, no, this is what I need. This is what I need, and this is what I need. Do you see this? So generally what? I wanted something that doesn't insist on this line. Will it be good on this line, yes or no? So I will be good if you give me either this line, or you give me this line, or you give me this configuration, or this. Do you agree? Does it matter which one? No, either one of them is good. So that's why I want a recognizer for first line, a recognizer for second, a recognizer for third, a recognizer for fourth line. So all the lines that are there, and then write the recognizers. So who's recognizer for line number 1?
P
and Q and R. Who's the recognizer for line number 4? P, yes, and the other one not. So P and the not Q and the not R. And then, who's next one? Q is good one. So it's not P and Q and not R. And finally, the last one is what? And R. Here it is. And can you do this no matter what circuit they want? Yes. So whatever they want, you need to kind of recognize what they want to write the appropriate table, and from the table to make a formula. Now, if we have a formula, can we draw a circuit? Yeah, so just do P, Q, and R, and then lead those at the end, connect them with R. I'm not going to draw it because it'll take the whole board, but I assume that everybody can do that. Then, of course, you know, if you start studying those circuits in your other disciplines, there will be many issues that we are here don't have neither time nor interest to address fully. There are many interesting questions. So what? This is the so-called standard disjunctive form, and that's a safe one. You can always write this. But in real life, you're not only interested to get something, you're also interested, for example, to have an economical model. Is this the simplest circuit that I can make? I'm not saying that. So sometimes you can maybe save and then maybe not make all connections. Maybe you can combine 2 of those, use distributive law, and make a simpler circuit than this one. And there are actually techniques, some Karnow maps and some interesting techniques that actually teach you how to simplify the circuits and make more economical ones. But that's not of interest to us. We just want to make it sure that using so-called disjunctive form, we can actually build always a circuit to do what we need. All right, what else is there? So here is the one. I did it with N and NOR. And then the same story as with formulas. Here are 2 circuits. And that a little bit addresses what I mentioned a minute ago. If you look at these 2 circuits, if you were to choose which one to construct, which one would you choose, left one or right one? Right. But of course, do they do the same thing? That means, do they, on the same inputs, produce the same outputs? So that means we say that those 2 circuits are equivalent. How do we check that?
Truth table.
Truth table, and the same way as before. So you recognize the formulas and make those 2 formulas, and then see if those formulas are are really equivalent in the truth table. So how would that look like? Let's make sure that we can read those. So what are the appropriate formulas? So formula 1. So what is the formula 1? How do we record this upper one? Not P and whatever's there. And whatever's there. Not what?
No, not P and Q.
P and Q. You see how P was let down there. So you have negation of P and Q on the bottom. And that's what, yes. So here we connected P and Q. P and Q. Then, oh, not P, yes.
The negation of not.
Oh, and here it is, true, because it was connected after the inverter. So if I connected it here, then it would be P, do you agree? But this was connected after inversion. So that's not P and not P and Q. Very good. What is the formula phi 2?
Not P or Q.
Negation of what? P or Q. So question is, are they equivalent? Now we are just checking if two formulas are equivalent. We can do truth tables, or can we do transformations, yes or no?
Yeah.
So let's see. So phi 1 is equivalent with what? Not P and if I go with negation through using De Morgan, what do I get? P or not Q, which is equivalent. Now I want to distribute. I'm going to get not P and P, or not P and not Q. But not P and P is always false. So it's false or not P and not Q. False or someone else is someone else. Whatever you do, I cannot help you. So if you are true, it will be true. If it's false, so whatever you say, that's how you go at this. So this is equivalent to not P and not Q, which is equivalent. You pull negation out, P or Q, which is exactly your phi 2. So are they equivalent? Yes, they are. So what is that telling you? That if you are asked to do this, actually you can do a much simpler circuit that does exactly the same thing, and there is no reason to spend more material on your circuit. All right. By the way, I mentioned that this is more curiosity. So if you, for example, don't want to buy too much material for your circuit, you only want to buy one device, either a device that describes all the others. I talked about it the other day. Those terms that you can express everybody with those terms. What are they? So here it is. If you have the following device, look at this device. It's called Schaeffer symbol. So P, Schaeffer Q is basically negation of P and Q. And it's called NN symbol. Although people very often associate it with the name of a logician from the beginning of 20th century, Schaeffer. So what's interesting? This one, if you have this device, you don't need any other devices. All the devices could be described using this one. Of course, your circuits will be very, very long, and huge. But anyway, you can express everybody else. Why? How can you express a negation using Schaeffer symbol? No, if it's only one letter, of course, so it would be what? Negation of P, no, it's P Schaeffer P. Is this true? Let's see. If P is true, how much is true Schaeffer true? negation of the conjunction, so that will be negation of true, it will be false. Here is false. If you do false, what will happen? False and false will be false. Negation of false is true. Negation of false is true. Do they have the same value? So you can always replace not P. So instead of this, you can use this symbol, but you need to use the letter twice. But how would you then report P and Q? You need to negate it, do you agree? Because you want negation of the Sheffer. Because Sheffer is negation, you want one more negation to get rid of that extra negation, do you agree? But how do you negate something? Sheffer it with itself. So it would be P Sheffer Q Sheffered with itself. So this, and then what? If you want to check it, just check all the valuations. Let's do one. When P is true and Q is false, what is the left side? True and false is false. So let's see this guy. P Sheffer Q is negation of their conjunction, which is true. This is negation of their conjunction, which is true. T Sheffer T is negation of the conjunction, which is false, exactly as we showed. Then you can check all the other 4 lines. So Sheffer expresses conjunction. Can now Sheffer express disjunction? Yeah. Yes, because now disjunction goes what? P or Q is negation of not P and not Q for De Morgan. And then P implies Q could be expressed as not P or Q. And equivalencies, of course, so everybody could be expressed using Sheffer. And then there is the other little device that can express everybody, and that's called NOR, or Lukasiewicz by name of Polish logician from the same period. P is negation of P or Q. And by the way, these are the only two devices that can do everything by themselves without any other devices. What's it? NOR, yes, but I don't call it NOR, you call it NOR. NOR, yeah. Very good. Okay, we played with that. This is, not something that's really important. This is more like curiosity if you ever hear about it or if you ever mention it. So if somewhere, you are faced with the need to express everything with one symbol, theoretically, these are the only two. There's no third one. These are the only 2 tables that can cover everybody else. All right, that's what we had in section 1.4. What are we going to do in the next section? We want to see how are we going to use this to add up the numbers. So for that, we need to represent numbers in binary form, and then to use binary form, to use our digital circuits to actually perform operations that we want to be performed the way we announce them here. So we'll get more specific for number calculations after the break. So let's continue at 2:35.